Hello and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and today we're going to be doing unit number 12, lesson number 3 on planes and lines in space. So when you study two-dimensional analytic geometry, i.e., geometry that's done with coordinates x and y, very often the first thing that you study seriously in algebra are the equations of lines. The equations of lines in three-dimensional space are actually considerably more complicated, and they require the understanding of vectors and parametrics and things like that. Planes as well are a little bit confusing, and one could really consider them to be the three-dimensional version of lines. So we're going to start with planes because, strangely enough, I think that they're actually a little bit easier to understand. Now remember, the assumption if you're sitting in Math 4 Honors is that you've seen planes before. You saw them in Algebra 2 with Trigonometry Honors. So a little bit of review, a little bit new. Generally speaking, the form of a plane in three-dimensional space looks like this guy. AX plus BY plus CZ equals D. Oh, I love the green. Where at least A, B, or C must not be equal to 0. In other words, if all three of them are equal to 0, what do you really have? But it's okay to have one of them. It's okay to have two of them. It's okay to have all three of them. It's okay to have numbers besides 1 in front of all three of them. The key is they have to be linear. So there can't be any terms to the second or any terms to the 1/2 or negative powers or anything like that. Go back to blue. I don't know how I got into the green. That's the key, right? Now, it's kind of hard when you just have still pictures like these two to even visualize what a plane looks like, but we all know what a plane looks like, right? It's a flat surface, right? And it's amazing that we can describe it with this linear equation. Okay, so what we're going to spend at least the front side of the worksheet on is trying to understand the different types of planes, how to think about them, how to sketch them, which is very, very difficult, at least for me. I'm sure the artists in the room would do a better job. Anyway, I'm going to clear out the text, and let's take a look at our first problem. All right, so there's all sorts of different types of planes. There's one where all three variables occur, ones where only two of the three variables occur, ones where only one variable occurs. This is very analogous in two-dimensional work for when we have things like equations of lines that involve both y and x and are slanted, and ones that involve just y or just x, and then we get our horizontal and our vertical lines. I think that the key to understanding how to sketch all of these things is first and foremost thinking about their intercepts. Of course, we've done this before when we've analyzed surfaces, but the x-intercepts of this can be found by setting these two variables equal to 0, right? In which case we would get 2x is equal to 12 and x is equal to 6. We can find each one of the intercepts this way, so the y-intercept would end up being 3y equals 12, so y would be equal to 4. And the z-intercept, trying to save myself some space, would be setting 2x and 3y equal to 0 and getting z equals to 2. So if we draw, or if we attempt to draw our plane, the first thing that we might do is come out here and plot an x-intercept, whoops, not at 2, okay, 3, 4, 5, 6, a y-intercept at 1, 2, 3, 4, and a z-intercept at 1, 2. Now, there's a really good question about what we should connect these with. If I wanted to just skirt the issue, I'd say, okay, just draw lines between them, and then that gives you a sense for the plane. And that definitely would work. The key is, let's just think about down here in the xy plane, right? What would connect these two? Well, if I just set the z-coordinate, let's say, equal to 0, which it is down here, then what happens, and actually let me kind of do this in color so that that didn't work out very well. Let me do this thing in color in green. Right, let's say I set z equal to 0. Then what would happen is all I would have is this equation, right? And that's the equation of a line, specifically the line 2x plus 3y equals 12. If I graphed that line, it would look like that. Likewise, if I set, let's say, x equal to 0, that would mean that I'd be in this sort of horizontal YZ plane. What it would mean is I'd have the line 3y plus 6z equals 12. And that would be this line. Well, that doesn't really look like a line. Let me go with one more. Let's see how the yellow works. We haven't done that very much. Oh, that doesn't work very well at all. So if I set y equal to 0, we're still going to stick with it. We would get 2x plus 6z equals 12. That's also a line, specifically this one. I do like the colors, though. I'm going to go back to blue, and then this would just kind of get filled in. Now, just like a line, a plane extends, right? It kind of extends off in these directions forever. We'll take a look at a computer image of that in just a second, okay? But I think I've done a poor enough job at this point to give you a sense for what it looks like. Let's take a look at one where there are two variables. This is probably the hardest one for people to really get a sense for. But what I'd like you to do is pause the video now and find the intercepts. Find the x-intercepts, find the y-intercepts, and find the z-intercepts, okay? All right. Well, I hope you got a little bit confused on that one. Okay, and let's take a look at why. Confusion is a good thing in math, right? To find the x-intercepts, I'd set y and z equal to 0. That would knock this out, and I'd get x equals 4, no problem. To find the y-intercepts, I'd set x and z equal to 0, so that would be gone, and I'd get 2y equals 16, and y would be 8. And to get the z-intercepts, I'd set that equal to 0 and that equal to 0, and I'd get 0 equals 16. But that would indicate to me that there are no z-intercepts. Why? Because 0 can't be 16. It's pretty simple. A lot of times math sometimes gives you things that seem really weird but tell you really good information, like, hey, the z-intercepts are the numbers that make 0 equal to 16. Okay, there are no numbers that make 0 equal to 16, so there are no z-intercepts. Anyway, let's do it. We've got our x, our y, and our z axis. We're going to come out and we're going to go 1, 2, 3, 4. Right? Yeah, okay, got it this time. 1, 2, 3, 4, 5, 6, 7, 8. Now think about this. If I just asked you to graph this in XY land, it would be this line. So that line must still be on there. But the key is, and actually let me extend the line. Let me go like this. The key is just like a vertical line in 2 space, right? Now what I have is a vertical plane, right? So I've got this plane that runs parallel to the z-axis. All right, and I can get a sense for that by looking at the line that it creates in the xy plane. Wow, these are great pictures, aren't they? Okay, let's take a look at z equals 4. All right, so z equals 4. What does that even mean? Right, that means that any point where z is equal to 4 lies on there. So for instance, 0, 0, 4, or negative 1, 3, 4, or 5, 7, 2. Oh wait, no, that doesn't lie on there. Z isn't 4. But if I erase that and put a 4 in there, it does lie on there. Right, so this is very analogous to horizontal and vertical lines in two-dimensional space. Right? This is a horizontal plane. Very hard for a person like me to draw this. I know its z-intercept is right there, and then what happens is it's just this plane. Right? Now remember, planes aren't rectangles, but it's this plane that simply is 4 units, always, above the xy plane. Right? So it's the xy plane that's been lifted up 4 units. You know it's sad when that's the best picture so far of the day. Okay, x equals 2, this is going to be way worse. It's very similar to z equals 4, right? Except points like this are on it. Doesn't matter what y or z are, x must be equal to 2. Right about now, my head is covering up something on the page. Please excuse that. Filling it up. 1, 2. So I know that point's on there. And kind of like the z, the key is, right now, I'm going to draw it as a rectangle. I've got this plane that is always 2 units away from the YZ plane, right? So this is a vertical plane, but then again, this was a vertical plane as well, right? A plane that kind of was standing up like a board. This is a horizontal plane. The only types of horizontal planes are ones where Z is equal to a constant. Vertical planes can take all sorts of different sort of forms, ones that are parallel to the YZ, parallel to the XZ, or kind of slanted like the one in letter B. All right. Now, again, is it that important to be able to draw these well? Not really. What is important is that when you see something like x equals 2, you have to kind of think of that as, okay, that's a board, right, that I'm holding vertically, right? And I can almost think of it as a knife that I could use to slice things, right? We're going to have to do that eventually, tomorrow in fact, right? Vertical is even more important. The z equals, right? Those are what created those level curves in the last lesson that we did, or their intersections created those contour lines. So I'm going to clear this out. All right. And then let's do the following. Okay, we're going to cover up a little bit of the text on the screen, but let's open up Grapher right now and take a look at these 4 planes a little bit better. All right, I'm opening up now. All right. We'll just go through them one by one. Right, letter A was the plane 2x plus 3y plus 6z equals 12. Let me click on that one. All right, there it is. One of the things that's kind of tough about this program is that I've zoomed in enough, or I've zoomed out enough so that we can see all the intercepts, but now the axes actually go by 2 units, and if I rotate it, you can kind of see that, right? You can see whereas the x-intercept was supposed to be 6, it looks like it's 3 now. The y-intercept was supposed to be 4. It looks like it's 2 now, etc. All right? But just keep that in mind. But you can really kind of see that. It's hard to see the sort of triangle picture that we drew, but you can kind of imagine it. All right? Let me unclick that. All right? Let me click on the second equation, which was that 4x plus 2y equals 16. I'm really glad that I have this one graphed now. Really, you can take a look at this thing. You can see that it's a completely vertical plane, but you can also see that it runs nicely parallel to the z-axis, right? The z-axis will never hit it because it's this board that's kind of, set upright. All right, let me click and get out of that one. The last 2 are going to be kind of less remarkable looking, but I think even more understandable. Let's click on the z equals 4. We've got a nice checkerboard picture here. And if I rotate this in a variety of different ways, you can definitely tell that that's a plane that's 4 units up, especially if I zoom in to make sure that the axes are all sort of scaled by 1s. All right. And let's take a look at what that vertical plane looks like, x equals 2. In fact, let me leave the z equals 4 on there just for a second. Let me click on x equals 2. Isn't that kind of neat, right? We've got this horizontal plane, this vertical plane, right? Yeah, kind of looks neat, right? You can tell that. So planes, very hard to sketch by hand, really neat to visualize, I think, when you're looking at it on these 3D graphers. In fact, let me put Grapher away now. All right. And let's move on to one more question about planes before we go on to lines. Okay, little multiple choice question. Why don't you go ahead and read it, pause, and then see what your answer is. All right. So it says, which of the following planes runs parallel to the z-axis, and how can you tell? Well, the answer is this one. And the way that you can tell is that because it has no z-intercepts, right? If you tried to solve for the z-intercepts, you would set x equal to 0, and you'd set y equal to 0. And what you'd get is you'd get 0 plus 0 equals 12, and 0 equals 12. And of course, no, it doesn't. Therefore, there are no z-intercepts. Therefore, it must run parallel to the z-axis. Now, little red. Careful. That's not how you spell careful. Actually, you know what I'm going to do? Change that into a little dot. Okay, careful. A lot of students pick up on a pattern. They say, well, okay, I know it's got no z-intercepts. I know because z doesn't show up in the equation. All right. Yeah, so yeah, z's not there. Great. Okay, good guess. Wonderful. All right, here's the problem though. Let's say I took this equation. All right. Z also doesn't show up in that equation. Question is, does it run parallel to the z-axis? How can I tell? Well, again, if I did the intercepts, what I'd get is 0 plus 0 equals 0, and 0 equals 0. Why, yes. That actually means that all z values are correct. Now think about that. What does that mean? Right? Every z value hits this plane. And what that means is that this plane actually contains the z-axis. It looks something like this. I'm going to kind of extend this a little bit. X, Y, Z. I'm going to go in a different color. I'll go to red. Basically, what it looks like is it kind of looks like this. All right. And of course, it extends downward as well. I'd encourage you on another graphing program. Literally, the z-axis lies in this plane. So we wouldn't want to say that it runs parallel to the z-axis. Here's the bigger point. Don't rely on gimmicks, right? You know that something runs parallel to something else if they don't intersect, right? And how do you know they don't intersect? It's not about z being there or z not being there or x or y or whatever. It's about looking for an algebraic condition, right? Let me solve for the z-intercepts. And if there are none, because something weird happens, like 0 equals 12, then awesome. On the other hand, if I get 0 equals 0, then I have to interpret that in a different way. All right? And that can be tricky, very tricky. So I'm going to clear this text out. All right? And we are going to now talk about lines in 3 space. You have learned about lines for so many years in 2 space that if I say, picture the equation of a line in your head, you typically will think of like y equals 2x minus 7, something like that. All right. But how much have you really thought about them? And exercise 3, I want you to really think about this for a moment. It says, how many dimensions is any curve? How many independent variables can it have? So not just lines, but any curve. How many dimensions does it have? Pause the video now and think about this. All right. A lot of students, when I ask how many dimensions any curve will have, they'll often say 2, you know. But all curves are one-dimensional. All surfaces are 2-dimensional. All solids are 3-dimensional. The way you can really think about dimensions, I think, is if you're sitting on the object. The question is, how many independent directions can you go? Independent. So you might say, well, I could go one of 2 directions. Well, no, they're not independent because this thing's just anti-parallel to this. On the other hand, if I was on a surface, so let's say that this is some surface hanging out in 3-dimensional space, if I was at a given point, I could either go in this direction along the surface, or I could go perpendicular to it. So that's 2 dimensions, right? Likewise, if I'm in 3-dimensional space, if I'm in a solid, I don't know, let's say that we got some sphere, right? So this thing's a solid, right? Then, of course, I can go in 3 independent directions. I can go head this way, head this way. I'm not on the sphere now, I'm inside of it, let's say, right? Anyway, so curves are one-dimensional, and that means that there can only be one independent variable, right? And this is kind of cool, and it's, I have to say, sort of deep. Deep to the point that it's probably not going to even be possible for me to really explain it to you in a great way. But if you can only move in one direction, right, then there's got to be one independent variable that kind of controls which direction you go in, right? On the other hand, if you've got an x and a y as inputs, as independent variables, an x and y as an input, right, well then you can go sort of north-south or east-west, and that generates a surface that has area. All right. The reason that I'm pointing all of this out, and let me clear this, is very, very important. All right. When we think about lines in 3-space, there can only be one independent variable. It's why an equation like this, z equals, let's say, something very simple, x plus y, must represent a surface. It can't represent a line, even though it's linear, because there's two independent variables. Two independent variables. So let's take a look at how we form lines in 3-space. All right. We have to go back to using parametrics. So exercise 4 says find one possible set of parametric equations for the line in 3-space that passes through the points ... Verify that the line passes through the 2 points given. All right, so here's what we're going to do. All right, we have to go back to parametric with t. We're going to calculate delta x, we're going to calculate delta y, and we're going to calculate delta z. All right, obviously delta x, x grows by 5. Delta y, y shrinks by 2. And delta z, z also shrinks by 2. Okay, now back in parametric, when we were doing this in 2-space, remember, we always had equations that kind of looked like this. x1, plus at, y1 plus bt, and now what we're going to have is z1 plus, let's say, ct, right? Where a, b, and c were some vector that just simply pointed in the direction that the line has to go. Well, an excellent choice for that vector would be 5, comma, -2, comma, -2. That points in the direction I have to go. I need to go 5 in the x direction, -2 in the y direction, and -2 in the z direction. All right, sorry, that's my x, y, z kind of frame of reference. 5 this way, 1, 2, 3, 4, 5. 2 this way, 1, 2, and 2 this way, 1, 2. Picture not drawn to scale. So it's actually very, very easy to create the equation of a line in 3-space. Get rid of this, right? All we have to do is say x equals -3 plus 5t, y equals 2 minus 2t, and z equals 10, also minus 2t. Now, just like the equations of parametric lines in 2-dimensional space, all right, here there's an infinite number of correct choices. We're just trying to come up with the line, not the line segment, you guys. So those of you that struggled with that whole t goes from here to here, don't worry about it so much. We're just trying to come up with the equation of the line itself, and here it is. It does say verify that this line passes through the 2 points given. All that means is that we have to find t values that give us the 2 points. But that should be easy. Pause the video for a minute and try to figure out if you can come up with the t value that puts you at -3, 2, 10, and the t value that puts you at 2, 0, 8. Pause the video for a second. You should be able to do that. All right. I didn't give you much time there to pause because it should be pretty easy, especially this first one. T equals 0 would knock all of these terms out, and we'd be at that point -3, 2, 10. And it doesn't take much to figure out that t equals 1 will put you at this point, because that will allow me to add 5, subtract 2, and subtract 2, which is what I need to do to get from one of the points to the other. All right? Really, really simple. Really simple. So especially if you did parametric equations in 2D. If you didn't, then you're probably looking at this wondering what in the world I'm talking about. Sorry. I'm clearing it out. All right, let's go on to another problem involving lines in 3-space. I think this one's going to be pretty easy. It says find one possible set of parametric equations for the line in 3-space that is parallel to that vector. So they're just giving me the parallel vector. There it is, -4, 2, 8, and passes through the point 2, -3, 1. Then it asks, does this line also pass through the point -10, 3, 17? So what I'd like you to do is I'd like you to pause this video right now and see if you can work through the whole problem. You've got everything you need at this point. Take 5, 10 minutes, whatever you need. Really, really think about it, okay? All right, let's do it. First part of the problem, I hope,
please excuse this
is
interruption.
fairly simple.
At this time, we would ask that the following groups make their way to the auditorium for the senior assembly.
Do I try to talk
All
over my
seniors
principal?
escorted by their...
Okay, let's take a look at the equation on the line. It's easy. We're only given, we're only given one point that lies on the line, so we have to be good about using the 2, the -3, and the 1, but then they just give me the vector, right? It's minus 4t plus 2t plus 8t. See, one of the really fascinating things is that in two-dimensional space, you can get away with writing the equation of a line without using parametrics because the slope, right? So this is just a little sidebar. The slope, delta y divided by delta x, really encapsulates that vector. And really the vector is delta x, delta y, or any scalar multiple of it. But the problem, though, is in three-dimensional space, we really have a three-way ratio. It's delta z to delta y to delta x, and not in that particular order, mind you, although I think that order makes some sense. Doesn't really matter what these numbers are, as long as they're in this ratio. So, one thing we could have done is divide all of these things by 2. Shoot, we could have divided them all by 17, and it still would have been fine. Okay, so that's the first part of the problem. The second part of the problem asks us, does the thing pass through this point? And there are so many neat ways to do this problem. So many neat ways to do it. Let's explore 2 ways right now, because I don't know what you did. Here's one way to do it. One way to do it is figure out the amount of time, let's say t is time, it would take for the particle, or for the line, to reach this point. So what we would do is we would solve 2 minus 4t equals -10, -3 plus 2t equals 3, pardon me for that, and 1 plus 8t equals 17. I'm going to do this really quickly. -4t is equal to -12. T is equal to 3. Here I'd have 2t is equal to 6, and t is equal to 3. And here I'd have 8t is equal to 16, and t is equal to 2. So the answer is no, right? It doesn't lie on that line. If it lies on that line, there has to be a value of t that gives me that point. And 3 would give me the first 2, but only 2 would give me the third one. So no, that's one method. Here's another cool method. I like this as well. All right, let's say, sorry that I need the room. Let's say that I take the point 2, -3, 1, and I look at moving it to the point -10, 3, 17, right? I have a delta x that's equal to what? -12, a delta y that's equal to +6, and a delta z that's equal to +16. So if I look at delta x to delta y to delta z, of course I'm now going to completely ignore what I set up there. I get -12 to 6 to 16. The best I could do is reduce that by 2, so that would give me -6 to 3 to 8. But I need something that has this ratio, -4 to 2 to 8, right? These aren't the same ratio. They're just not. In fact, if I wanted to simplify this, I could say it's -2 to 1 to 4, right? This is ultimately the ratio I need. Since these two ratios are identical, then the point doesn't lie on the line. That's very similar to those problems in 2 space where they would give you 3 points and they'd say, are they collinear? So you would figure out the slope between these two. You'd figure out the slope between these two, and if m1 equaled m2, well, then they were collinear, and if they weren't equal, then they weren't collinear. All right, so it's a neat point. It's a neat problem, I think. Anyway, I'm going to clear this out. Okay, let's go on and do the last problem. Exercise 6. Does the line in 3 space that contain those 2 points also contain that third point? Justify your answer. Again, based on the previous problems, I think you have everything you need for this. So pause the video now and see what you can do. All right, let's take a look. Again, lots of different ways to do this. One way is to generate the equation of the line between these two. I'm going to kind of do that on the fly, okay? So it would be 4, -2, -1. My delta x was 2. My delta y was 10. And my delta z was 5. So this is the equation of the line. Now what I could do is set that equal to -4, -42, and -21, and I could solve. In this case, I'd have 2t equals -8, and t would be -4. In this case, I'd have 10t is equal to, wait, something went terribly wrong there. Hold on, 4, -2, -1, because I know the answer is yes, and yet something is going wrong. Help me find it. No, it's not going wrong. Here I'd have 10t equals -40, and t would be -4. Ooh. And here I'd have 5t is equal to -20, and t is -4. So the answer would be yes. We could also look at it from the perspective of how we did the last problem. We could say, all right, if I take 4 to -2 to -1, and I move that to 6 to 8 to 4, and then let's say I move that to -4 to -42 to -21. Well, let's take a look. Here I have delta x, which is 2. I already did this. Delta y is 10. Delta z is 5. So I have 2 to 10 to 5. Here I have delta x equals, -10. Watch that. Delta y equals, wow, -50. And delta z equals -25. Delta x to delta y to delta z is going to be -10 to -50 to -25. But if I divide all that by -5, I'd have 2 to 10 to 5, and that's the same ratio. That's it. So it's kind of cool. We can directly extend methods that we learned probably back in geometry, with thinking about whether points are collinear or not, to the three-space case. That sounded a little weird. Anyway, I'm going to clear out the text, write down what you need to. All right, it's gone. Let's finish up. All right, so we're getting near the end of the course. One lesson left. That's it. That's weird to say. But let me remind you that this has been an Arlington High School Math 4 Honors lesson. We're in unit number 12. We just looked at planes and lines in space. Until next time, keep thinking and keep solving.